Okay, so once again, I extend a warm welcome to all of you to day 3 of the user preparation webinar on next generation EUMETSAT spectral images. So the flexible combined imager FCI on board MTG and the METimage on board EUMETSAT's next generation polar orbiting satellite EPS-SG. I'm Sri Rekha Thoniparambil and I am the EPSSG User Preparation Manager, and I organize this webinar together with my colleague Stefan Bijinski, who is the MTG User Preparation Manager. And like I said, this is day 3. So if you have joined day 1 and day 2, you know that on the first day we talked about FCI instrument on board MTG, where we talked about the overview of the instrument, the level 1 products, the product generation, formats, dissemination, application perspectives, looking at RGBs, etc. And on day 2, we had a similar journey through METimage. And today we take a step ahead and we go to geophysical level 2 products from both FCI and METimage. And I have to mention that these are the products that are generated at EUMETSAT headquarters at the central facility. And as you know, there are lots of products generated by our SAFs, the EUMETSAT satellite application facilities. And we would organize another webinar in the future to take into account these products. So with that, I think we should start the session, but a few points before that. During the event, please ask, like the previous days, use a Slido tool to ask questions to the speakers. So just type slido.com and use the event code. I think you will see that in the chat message now. It's NG, capital N, capital G dash capital I images. And you can type this on your computer or smartphone and use this as a medium of interaction with the presenters and among yourself. So you can post your questions, you can post comments, etc. Everything is welcome. And use the Zoom chat for any technical issues. We will try to solve them as much as we can. Also, just be reminded that we will take up the questions during the Q&A. You will see in the agenda, there's about 10 minutes for Q&A for one session. And we try to take as many questions during this time. And if not, we will we'll try to answer, we will definitely answer them and provide you with the slides, the Q&A, and also the recording of the session to all registered participants. Yes, and one more point about breaks. We got feedback from day 1 and day 2 that the breaks were too short. So we decided that we will give a bit longer break. I can understand that very well. So, the plan is to give a 3-minute break after the first talk and a 5-minute break after the fire product talk. So there was a comment that you would like to go through the Slido questions as well. So I think this should be enough. Otherwise, we would run late in the evening. Okay, so with that, I give the screen to Johan. Johan, can you start?
Yes, 1 second, just share. There you go, I think. Let me know if it doesn't work.
Johan, we are seeing, yeah, that's good. That's good. Yes. Start.
Then, hi all from my side. I'm happy that you are tuning in for this presentation. So I'm Johan Strandgren, and I'm working as a remote sensing scientist at EUMETSAT, focusing mainly on the level 2 products from the geostationary imagers. But today I will give an overview of the FCI level 2 products and also METimage. So as a short outline, it's in principle 2 parts. So first I will go through the level 2 product from FCI. So it's in principle 1 slide per product, just to give a few bullet points, some key information on the different products, and then the same for METimage. You can see some products are in bold font, and that means there is a more in-depth presentation on this product in the subsequent talks of my colleagues. So let's start with the first one. So that's FCI Cloud Mask, CLM. And I should also start by saying that the Cloud Mask and the Cloud Analysis products from FCI, so that's cloud mask itself, cloud type, and also the cloud up temperature and height products, they are based on corresponding algorithms from the nowcasting staff, severe algorithms. And therefore also the figures you will see on the right side for the first 3 slides are showing nowcasting staff products from severe. So it's just as reference because it's very similar, but still the EUMETSAT headquarter products that I will present. So what you get with a cloud mask is a clear or cloudy clear sky mask indicating whether you have meteorological clouds, dust clouds, volcanic ash plumes, and you also have information about if we have snow ice covered surfaces. And this is done using a bunch of threshold tests. So first there's a set of single tests that are used to identify clouds, and then there is another set of tests used for restoral. So setting cloudy tests to or clear pixels to cloud if it's not clear or the other way around, and also information on dust and ash. And this is done using a set of channels. So the VIS 06, 08, 1.6, 3.8, the one water vapor channel, and 3 window channels. So this is severe heritage. So from the start of operations, we will not exploit the FCI channels, the new FCI channels, but rather ensure continuity and use what is done now for severe. And the cloud mask comes in NetCDF in grid format every 10 minutes, and it's provided at 2.2 kilometer. So the native infrared resolution. And then we also have the cloud type, and this derived then for all the cloud pixels. So it derives first is sort of the main cloud type, which is a set of, I think, around 12, 16 different cloud types based on the altitude, opacity, transparency, and also if it's multi-layer, that's the upper figure you see. And then there's also another cloud type that is called cloud phase, which is a thermodynamic phase of the meteorological clouds, if it's liquid water or ice. And also in both of these products, we also have the information about dust and ash carried over from the cloud mask. So those will be also indicated or included in those products. And here it's very similar. Data is for the cloud mask, so 2.2 kilometers every 10 minutes, but no grips, only in that CDF format. Next one is the cloud up temperature and height. So this is then for all meteorological clouds, the cloud up temperature and also the geometric height, so in kilometers or the pressure height, so in hectopascal over the standard sea level, and also it provides the effective cloudiness. I should also note here that this is only provided for liquid and ice clouds, so it's not provided for dust plumes or volcanic ash plumes. And all of these 3 products will also, you get more details in the subsequent presentations. And also here it's 2 by 2 kilometers. You get it every 10 minutes, and it's also in NetCDF format. You can see here in the figure is one example how it looks from the nowcasting staff cloud up pressure drive for severe, because it's the EUMETSAT product is based on this one, so it will be very similar. Okay. So going on, we have the optimal cloud analysis, OCA, which provides information on cloud phase, optical thickness, also effective radius, and also here it provides information on cloud top pressure, temperature, and height. And here it tries to use all channels simultaneously. It's not always the case, but here Phil will give more details later on. And how it does it is that it uses an optimal estimation scheme in order to fit the cloud model that best represents the observation that we get from all these channels. And this also includes multi-layer clouds. We have, for example, ice clouds or liquid water clouds, or even if we have dust or ash, it can also derive information if we have a dust cloud over another feature or another cloud below it. Here it's also 2 by 2 kilometers, as the case for most products. And it comes in every 10 minutes and also in that CDF format. And on the right, you see one example. Again, it's from severe because that's what we have now running with a cloud optical thickness from OCA. Okay, next one up is clear sky reflectance map. So this is basically the clear sky reflect or the reflectances that we measure in the visible and near infrared channels, and they are averaged or accumulated over a period of time. Normally it's 7 days, and then after 7 days they are averaged and sent and disseminated out to the users. And also it's not only the reflectances, but also you get information about the viewing geometry. So it's averaged reflectances as well as averaged viewing angle, solar zenith angle, relative azimuth, for example. I should also mention here that there is no corrections applied, like atmospheric correction or viewing angle corrections. So what you get with this product is what FCI would see or what it would measure for a day in case there would be no cloud on, over the Earth. So here we have high resolution, so 1 by 1, since we use the visible and infrared channels. It's only provided every 2 hours during daytime hours, but the file format is the same. So it's again that CDF. And on the right, you see one figure, one example that is currently running for Siberi. Next one up is the all sky radiances. So here it derives statistical information on the first of all radiances, but also in case of visible near infrared channels, the reflectances, and in case of infrared channels, the brightness temperatures for all the 16 FCI channels. And this is a segmented product, which means that it looks in a field of regard. If it's always at nadir, it's 32 by 32 kilometers. So in case of visible near infrared channels, it's 32 by 32 pixels. And in case of infrared channels, it's 16 by 16 pixels. And then it looks in this field of regard and it computes the mean radiance, reflectance, brightness, temperature, standard deviation, minimum and maximum, and provides the information. And it's also provided in 6 different categories. So you get it both for like all pixels within this field of regard, the 32 by 32 kilometers. You also get it for all the clear pixels in this area, the cloud pixels. And if you have, in case of cloud pixels, it's also divided in different subgroups like low level, cloudy pixels, mid level, and high level. And again, we have here one example how the ASR looks from Severe that is currently running. So you can see there it's a bit coarse resolution due to the segmentation. So yeah, resolution 32 by 32 kilometers at nadir, comes in every 10 minutes, comes in net CDF and also in buffer format on GTS. Okay, and then new for FCI is the outgoing long wave radiation. So this is essentially the spectral radiances that we have from the infrared channels that we convert to spectral fluxes, and then these are combined into a total flux. So you get, yeah, the total outgoing long wave radiation that is emitted by the Earth system. So here we use the infrared channels, but we exclude the 3.8 channel because of the solar contribution. And here you have also one example how it looks for one example seen from Siberi. And this is also the infrared resolution, so 2.2 by 2 kilometers. Comes every 10 minutes and in the format net CDF. And then we also have the fire detection algorithm, FIR. And this one first derives a fire probability map. So we have for every pixel fire probability. And it also provides flags for low probability fires, high probability fires, and medium probability fires. And also, as was mentioned on Tuesday, the 3.9 channels has improved dynamic range compared to Severe. So this in addition to the higher spatial resolution, should give a very much improved fire detection capability with FCI compared to Severe. So for Severe, you see on the image on the right, there is one example from Severe. And there is a difference because here we have like 2 classes, possible and probable fires. But with FCI, this will be replaced then by low confidence fire, medium confidence fire, and high confidence fire. So it will be essentially 3 different flags in addition to the full disk fire probability map that will be at pixel resolution. Yes, this is a 2 by 2 kilometers again, every 10 minutes, so every repeat cycle. And it comes first in NetCDF format, but it also comes in the common alerting protocols format. And then we have the global instability index. So this provides different proxies for atmospheric instability within, again, it's a field of regard, so a segmented product, but here it's 3 by 3 products, or 3 by 3 pixels, sorry, so 6 by 6 kilometers. And what we get is lifted index, the K index, the total precipitable water, and also the layer precipitable water into 3 different atmospheric layers. So what we do is that we take a nowcast or a forecast profile of humidity and temperature, etc., as the first guess. And then there is an optimal estimation approach in order to modify those profiles in order to match and simulate with the transfer simulations, satellite observations, and optimize those profiles in order to match our observations as good as possible. And then when we have those profiles of temperature and humidity, then we compute those indices and precipitable water. And this is retrieved only over clear sky scenes. As you can see on the figure on the left, on the right, sorry, you have one example for severe decay index. So you have missing data, of course, over cloud areas where you don't have the information. So as I said, this is now at 6 by 6 kilometers, not at the full pixel resolution, but still it's every repeat cycle, and it's disseminated in NetCDF format. And then we also have the total zone, and this is basically, or it is derived in the same algorithm as the global instability indices, which also derives, or in the optimal estimation scheme, it also optimizes the ozone profile. So when the GI algorithm has finished, you simply take the ozone profile that has been outputted and integrate the ozone concentration, or the ozone concentrations to get the total atmospheric ozone. And this again over clear sky scenes, but also over warm clouds. So there would be either low clouds or optically thin clouds. And since it's the same algorithm as the GI, it's also 6 by 6 kilometers and every repeat cycle, and it's again in NetCDF format. And the final product for FCI is atmospheric motion vectors, which provides position, speed, direction, height, and quality of wind vectors. So what it does is that it derives the position relative motion of different tracking targets by comparing multiple images from multiple repeat cycles, and in order to track them. But here I won't go into detail because Regis will give a dedicated presentation on this product later on today. And here, yeah, spatial resolution is not really applicable, but it comes every 30 minutes because it needs 3 repeat cycles. And it's in NetCDF, but also on the GTS in buffer format. Okay, and this quick overview, more as a reference, you have a table here showing what is disseminated for severe at the moment and what will be disseminated for FCI. So the main purpose from the start of operation is to ensure continuity, but with more channels and enhanced channels with FCI, we will have in the future also use this in the algorithms and also implement new algorithms. And as Rika said also in the beginning, there's of course also a broad suite of additional products generated by different satellite application facilities. Okay, and then we have the EUMETIMAGE products. So I think I have to speed up a bit. But here we have a cloud mask also. So it's also based on thresholds tests. So some cloud reservoir tests, some AVHRR heritage tests, and some new tests exploiting the new channel information compared to AVHR. And here you will see more details by Loredana later on. But here it's at 500 by 500 meter resolution and in NetCDF file format. We also have a cloud pressure retrieval using the oxygen A band, but the observations near the oxygen A band, so around 0.7 microns. And also retrieves, in addition to cloud pressure, also cloud optical thickness. You can see one example in the image here in RGB, and amplitude or cloud top height retrieval. It's also 500-meter resolution at nadir and in NetCDF format. And here, Alessio will later on give more information. There's also for METimage also the OCA product. So it's essentially the same. So I will just keep this as a reference. It's the same algorithm in principle as for FCI, and you will get more information later on. And then there's also the total perceptual water algorithm for METimage. And there are two approaches. One utilizes the visible channels or visible infrared channels using a one-dimensional variational method. And then there's also an infrared approach that uses the infrared observations, and this uses similar retrieval approach as is used for the global instability indices for FCI. So those retrievals, they derive essentially the water vapor profile, and then this is then integrated vertical to get the total perceptual water. And this is segmented product, 3 by 3 kilometers. So 3 by 3 pixels, sorry, 1 by 1, 1.5 by 1.5 kilometers, and both in NetCDF format. And finally, we also have the polar atmospheric wind vectors. So this works very similar to the FCI AMV. AMVs, just that instead of having 2 consecutive repeat cycles, we take 2 consecutive orbits in the polar areas. So usually with a time lag of around 90 to 100 minutes. And then we can, again, track differences, track features in those images and derive information on wind vectors. And also here, Regis will give more information, but it's also provided NetCDF and buffer format. And also here I have a similar table for reference, what is disseminated from EUMETSAT for AVHR and what it will be disseminated from METimage. So here's also the point of having continuity, but also since there are some significant changes between AVHR and METimage, also from the beginning, we can exploit a lot of information from the new channels and with improved spectral quality and higher resolution with new products, etc. But there will also be in the future, after operations have started and continued has been ensured, also new products from EUMETSAT. And also here, of course, there will be also from the start a lot of products from the satellite application facilities. And with that, I thank you a lot for your attention and invite questions, and I will do my best to answer them. Thanks.
Thanks, Johan. I will bring up the questions actually in a minute. Yeah, I think the first question is maybe for later, right? The advantage of the TPW track compared to MODIS. Do you want to take it now, or do we?
I think most of those such questions are probably
answered for
later on.
Talk, yeah. What about the cloud top height talk? Do you want to take that now? How do you calculate the cloud top height from a satellite? Do you use RTM or is it an RTM independent product?
It depends on which product. I'm most familiar with FCI, but with the cloud temperature and height, it will also be explained by Hans Joachim, but that's depending on an RTM. So you first drive lateral pressure from the RTM, and then you go into the weather model and convert into height. That's it. The same is done for OCA, as far as I know.
Mm-hmm. And about the OLR for FCI, what is the combination of the IR channels based on?
Make sure I get the questions.
How do you calculate OLR for FCI? What's the combination of the IR channels based on?
Yeah, but the combination of the IR channels. So we use all IR channels that we have available, except from the 3.8, because it has strong solar contribution. And then we convert the spectral radiances to spectral fluxes. And then combine this from the all channels in order to cover the whole thermal infrared spectrum in the extent that we can cover it from the channels we have. And this conversion is done with some predefined regression factors that are scene dependent, but they are computed before.
Okay. Phil, I saw you raising hand. Yeah. Do you want to
I was just going to offer to help, but Johan answered the question. I think there's a spectral combination and then there's an angular combination. So there's two regression steps in there, two regression-based steps in the process. But yeah.
Okay, thanks, Phil. Why the high resolution visible channel does not provide data over the Asian region in the MSG Severi 41.5 degree, unlike IR data? I did not understand.
I mean, this is Severi. Severi is all channels 3 kilometers, except from the high resolution channel, which is a broadband channel. What I present is only FCI, and so far we only focus on the 0 degree operations, so not covering the Asian region and India. So I cannot really comment now on 41.5 for FCI.
Yeah, I think we can try to maybe get some information later and come back.
Yes, yeah.
Srika, can you hear me?
Yes, yeah. Is it Munir?
Yes. Hi, Munir speaking.
Hi, Munir, please.
I believe so that's the HRV channel. I believe there is a limitation of the bandwidth, and we cannot cover the full disk with the high resolution. So a different region has been selected.
Okay. I think that's a great answer. Which NWP model provides forecast profiles for the GIA products?
Okay, Phil, correct me if I'm wrong, but I think it's ECMWF.
Oh, okay. Since nowcasting SAP also derives instability indices, is GIA going to use the same algorithm or different?
No, this is a different algorithm. Yeah, it's only cloud mask and cloud analysis. They are based on the same approach as nowcasting SAP.
I think the fire question we can take maybe later, right? Regarding the fire products, would this product utilize the advanced? We have a fire talk. I think we can take that then.
Leave it for. Okay.
We will save some time. And for the GIA, because there's no talk on that, we can maybe try to answer it here. In GIA retrieval, you use 0.2K as a background error for RTM. Why this fixed value?
I'd say I'm not sure. I don't know. Maybe Phil, do you know?
Yeah, there's no reason for it to be absolutely fixed. It's true. It's never been tuned in that kind of detail. It's something we could look at, but I think that's just a pragmatic solution we've had in the system for many years now, probably.
Okay, good. Will all cloud products going to be distributed centrally instead of what is done today, where each center processes the nowcasting software?
I mean, this is a bit different because there is a nowcasting SAP suite of products. I think this will be done as it is now, that they provide a software and it's up to users to run it. And then there are the EUMETSAT products, of which 2 of them, the cloud mask, 3 of them, cloud mask, cloud type, and cloud top temperature and height, are based on nowcasting SAP approach. These will be disseminated from EUMETSAT centrally as official EUMETSAT products.
Yeah. Okay. These the Severi products will soon be discontinued. This is top of what's TOZ product? I don't know.
Total ozone. Yes.
Ozone. Severi product will soon be discontinued due to poor quality as demonstrated by EUMETSAT. Thanks to what improvement will the total ozone XCI product be declared better?
Yes, I think that's to be determined. I mean, the decision to discontinue the Severi TOS is quite recent, and of course the development of FCI TOS runs for a longer time period. So it will be disseminated in the beginning, and then we will see how the quality is, if the spectral and increased spectral resolution information is sufficient, but that's to be determined.
Okay. Why TPW for VIA are 2 separate products, one for IR and one for visible?
I think we better leave that one for Loredana. She will give a dedicated presentation.
I think that's the last question referring to CLM product, it was mentioned the continuity from Severi would be preserved, but it was mentioned as well that the nowcasting Ceph algorithm would be used. Could you explain in more detail? As far as I am aware, there are two algorithms for CLM in PEF, EUMETSAT and nowcasting Ceph.
Yes, so continuity refers to more in terms of which channels are used. So we use the same channels that are used for nowcasting Ceph algorithm for Severi, but it's true it's not continuity in terms of that in the sense that we are changing the algorithm. So the algorithm itself will indeed change from the cloud MPEF cloud mask to FCI cloud mask, but it's continuity in terms of what information we use in order. So we do not include new channels like near 1.3 that will be included later on, just to ensure continuity.
Okay. Okay, so the remaining questions we take for the specific talks. And thanks, Johan.
Yeah, thank you very much.
We take a 3 minutes break, like I said in the beginning. So now it's 14:32 in my clock. So we meet in 3 minutes, 14:35, the CEST time. Thank you. See you. Hi everyone, welcome back. I hope my sound is okay. Let's see if there's further problems. I wanted to switch to my headset, but then I thought that's too much complicated now. But anyway, we move on to the next talk by Hans-Joachim Lutz on Cloud Mask and Cloud Analysis product. And Loredana is also presenting together. They give a double act, but starting with Hans-Joachim.
So, hello, good afternoon, everybody. My name is Hans-Joachim Lutz. I am responsible for cloud mask, cloud analysis, but also for other products, sort of as an algorithm development expert. Starting with the FCI cloud mask, I will give an outline, an overview. Then how we do the cloud mask retrieval, the cloud type and cloud face retrieval, and the cloud height retrieval. And after that, Loredana will take over for the EUMETImage cloud mask retrieval. The FCI cloud mask and cloud analysis algorithm is mainly based on the nowcasting Ceph cloud mask and cloud analysis algorithm developed for MST Severi, with a few changes in adaptation to the EUMETSAT processing and input data. All results will be provided on a 2-kilometer basis for every repeat cycle, so every 10 minutes. And then the cloud type and cloud face is again based on the nowcasting Ceph, and we will have a cloud type, so different types of clouds, and also the cloud face, liquid water or ice, but also information about dust and ash. And last but not at least, cloud top temperature and height retrievals. It will be also applied to the pixels coming out of the cloud type and cloud mask retrievals. But also, I have to mention that pixels classified as broken clouds will excluded from the height retrievals. And we will also give no information about the height of dust or ash. As an overview, the CLM algorithm is based on a complex threshold technique using the channels mentioned in the slide. We have different steps. And the first step we derive with 16 different tests, independent tests, a first version of the cloud mask, and then we do in removal or restoral for dubious pixels where we are not sure when the tests are contradicting each other, etc. We also store not only the cloud mask itself, but also information which test has been applied on a pixel and which test has detected a cloud on a pixel. And of course, in future, we will exploit the new FCI channels, but for the time being, we stay with the settings used for Severi. Here I have a list of the tests. We gave it a name and we show the channels which are used for it, and the threshold setting, whether it's static with an N or whether it's a dynamic threshold with an Y. Dynamic threshold means for the infrared channels that we use ECMWF input, run it through RTTOF, and correct the data for pixel surface emissivities. For the visible channels, we use the clear scalar reflectance map as a background, which is also a dynamic data input because it's an average over 7 days, running average over 7 days. And you see on the right side the description, which test is very sensitive to which type of scene. We have also a test which decides whether a cloud is opaque or potentially semi-transparent. And then we have restoral tests which are looking in certain specific conditions like twilight, then restoring tests over clouds over land or over cold surfaces. We do a spatial filtering, and we do dust detection, ash detection, do a distinction between the both because they give similar signals. For the time being, the ash detection is not defined, fully defined, and we will sort of after day one, introduce an ash detection algorithm here. Here's a nice example. We have at the left side the measurement. It's for MSG, Severi. We have on the left side the infrared channel, window channel, and on the right side the corresponding total cloud mask. And we have examples for different tests. For example, test CMT1, which is a test where we calculate the sea surface temperature and compare it to climatology data over ocean. You see in white the cloudy pixels detected by that test, and in gray all cloudy pixels detected by other tests. And on the other side, the right side, you see for an example for the infrared 10.8 test. Again, this test is applied over ocean and land, and you see in white the cloudy pixels detected by that test. The same applies for the visible channel. In this case, we have on the left side the 0.6 micron channel, and on the right side the test result of the visible channel 0.8, which is applied over ocean only. The 0.6 micron channel is applied over land only. This is to enhance the contrast, because over land the reflectance of land surfaces is lower in 0.6 than in 0.8. We give out in the NetCDF output following information about the cloud state, the illumination conditions, the NWP parameters. So was it available? Was there an inversion or not an inversion? And we give, of course, some quality parameters. High confidence, for example, or reclassified by the restoral tests, or we have low confidence if we have a sunken area. And as you know, everyone who is dealing with cloud detection knows all these problems. Cold surfaces may be misclassified as clouds. Low clouds may not be detected, especially in low solar conditions and over both sea and land, and at night over land. Snowy grounds are not detected at nighttime and therefore confused either with low clouds or cloud-free surfaces. False detection of volcanic ash and dust clouds, missing dust clouds over land is a problem, or the non-detection of dust clouds. And different surface types bring difficult situations to detect clouds, like coastal areas or mountain areas. Going to the next point, which is the cloud type and cloud phase, and it's again applied to all pixels which have been detected as cloudy in the cloud mask, and the processing is split into 3 parts, which identifies fractional and semi-transparent clouds, give a general cloud layer height, so low cloud, mid-level clouds, high-level clouds, and separates them in different classes. And of course, the cloud phase, which is liquid water and ice, or the information of dust and ash from the cloud mask. The tests are based on thresholds again, and different channel combinations, and most of the thresholds are coming from forecast data, in our case ECMWF forecast data. Here's an example. Again, the algorithm is based on the nowcasting SAF cloud type, and we have an example for Severe here. And the part 1 fractional and semi-transparent cloud detection are applied to the cloudy pixels, which are not opaque, identified by the test in the cloud mask. So we apply that to the other pixels, and we distinguish between high semi-transparent, thick, mini-thick, and thin clouds, but also clouds over low, high clouds over low, or medium clouds, which is a typical multi-layer cloud situation. And we also identify fractional clouds. For the opaque cloudy pixels, we separate between very low, low, mid, high, and very high level opaque clouds. The cloud phase, again, there is an example from the nowcasting stuff for Severe. we try to identify the phase, especially water and ice phase. We have, of course, then also the information not processed because there is no cloud or there is no valid data, etc. Then we have water cloud, ice cloud, and in the separation it can happen that you cannot define the cloud phase. For the fractional clouds from the cloud type, the cloud phase is set to undefined. Yeah, semi-transparent clouds are generally identified as ice clouds. The information we provide in the NetCDF is the different cloud types, but also the information not processed because there was no data or etc. Then we have cloud-free land and cloud-free sea based on the findings of the cloud mask, land with snow or sea with snow and ice. Then we have the different types of very low opaque, etc., up to semi-transparent, high, thick, and semi-transparent, high, above, low, medium cloud. And of course, fractional clouds. And then again, the information of dust and ash is transferred from the cloud mask. And then we do also some tests whether it's just contaminated or an opaque, thick dust cloud or ash cloud. And of course, we have undefined cloud by the cloud mask. This information is also given. And of course, the cloud phase, again, not processed, water, ice clouds, dust, ash, or undefined. And we have some quality information on pixel basis. It's whether it's night, twilight, day, or sun glint. And on general basis, we have some information about whether the NWP data was available, whether the MTG parameters were okay, etc., etc. And the last step is the cloud top temperature and height. We have again cloud top height algorithm has sort of three different methods. For opaque clouds, we use the direct gradients method, but we apply this method to all cloudy pixels because later on, if the other methods are failing, we are going back to the direct gradients method, which will, for all cases, give us a result. As you know, the direct gradients method compares the measured and simulated radiances. Again, these are from profiles from ECMWF, forecast profiles running through RTTOF and providing us with the radiance profile. Then we have the intercept method, which are applied over a segment and tries to fit observed and calculated radiances of 10.5 and 6.2 micron channels. These are applied to clouds classified as semi-transparent in the cloud type. And the third method is radiance rationing method, which compares, again, measured and simulated radiance ratios at pixel level. And we use the 13.3 and 10.5 micron channel, but we can also switch to other channel combinations. They are applied to clouds classified as high and very high opaque in the cloud type, and also as a substitute for semi-transparent clouds if the intercept method fails, which is quite often the case. And again, as a fallback solution, we use the direct gradients method.
Yeah, Can you speed up a bit?
Yeah, because it's the
Sorry.
last slide.
Okay.
Or second last, it's not applied to broken clouds, dust clouds, and volcanic ash plumes. These are the output parameters. We do also a parallax correction, give the cloud a temperature, pressure, height. We have an aviation height, and we give the effective cloudiness. And again, it's ordered in the NetCDF product. So I will switch over to Loredana for her presentation.
Thank you, Hans-Joachim. So hi, everybody. My name is Loredana Spezzi, and together with my team at EUMETSAT, I'm responsible for the development of Cloud Mask product from EUMETimage. So the retrieval approach for Cloud Mask from EUMETimage is very similar to the one you just heard from Hans-Joachim, so to the FCI one. Here in the bottom of this slide, you see the spectral coverage of EUMETimage, which is very similar to the FCI one, with the exception of the few two channel around 0.7 microns, which are centered in the O2 A-band absorption. So the algorithm retrieving the cloud mask from EUMETimage takes in input the EUMETimage radiance and a number of auxiliary files which provide information about the forecast profiles of humidity and temperature, and also the properties of the surface like albedo, BRDF, emissivity at the given time of the observation. Starting from this auxiliary information, the first step of the algorithm is basically the simulation of clear sky radiance depending on the given scene. These simulations are done using RTTOF, and this simulated radiance represents the radiance, the threshold over which the atmosphere is probably contaminated by clouds. The subsequent step of the algorithm uses this clear sky information and the additional auxiliary files to check whether in the specific scene there are, let's say, complications. For example, presence of sun glints or coverage due to snow or ice, because the presence of this condition, of course, complicates the retrieval of the cloud mask. So further adjustments are needed. And finally, we go to the central step of the algorithm, which is the application of the cloud test. So what you see here in the table is basically the list of 13 cloud tests which are applied to EUMETimage measurement to get the cloud mask. Among them, you can recognize some tests very well known and used historically for cloud mask detection, like, for example, the first test, which is the gross infrared test based on the 11 micron, or the other ones, which are split window tests. But you can also identify specific tests like the O2 A-band absorption test or the 1.38 micron water vapor test, which are specifically for EUMETimage, and in the case of the 1.38 also, for example, for FCI, which were not available on previous masks, for example, from AVHRR. And they are supposed to improve the detection of, for example, the cirrus clouds. So once the tests are performed, there is a probability calculation. So for each test, the probability is calculated by measuring the distance between the threshold simulated by RTTOF at this step and the measurement of the given test. Then this cloud probability, the probability of each test are combined into a final probability following a decision tree approach very similar to what Hans-Joachim has already shown for FCI. And finally, we get the final cloud mask, which I would like to stress is not a binary mask because each pixel has a classification based on the cloud probability. So what you see here is in white, high probability cloudy pixel, and in blue, high probability clear pixel. But there are, of course, also cases in between, probably clear or probably cloud, which are fixed depending on ranges of probabilities. Now, the final product follow the standards adopted for all EUMETSAT, for all EPSSG products. So these products are already available in our website, from our website, of course, based on simulation. And there are also product readers available in Spectral in case any of the user is interested into starting exploring this product. So the product are NetCDF. They follow the climate and forecast metadata convention. The product name is on this type, and in particular, this identifier, VII02CLD, identifies the cloud mask. Each product contains 1 minute of data, so about 3,000 times 400 times 800 pixel, and the resolution is the native EUMETIMAGE resolution of 500 meters, while the SWOT is about 2,800 kilometers wide. The structure of the NetCDF, again, is the same as any other EPSSG product. We have 3 main groups: status, data, and quality. The status groups basically contain general information about the satellite and the instrument at the time of the observation, while the data in the quality group contains the variable specific for this kind of product. So in our case, in the case of the cloud mask, in these 2 groups, you find information on time of the observation, geolocation, geometry given at time points. And then for each pixel, you find a clear cloudy flag containing also information of possible ash contamination. But you find also the clear sky probability that goes from 1 to 0, and this allows the user to set somehow his own mask depending on the application. We have also additional information on the surface type, of course, for each pixel, and and a lot of quality indicator which help the user establish whether that retrieval is trustable or not for the given pixel. Pro and cons of this product. So the EUMETIMAGE Cloud Mask product are near real-time product, retrieved 24/7. The timeliness is about 15 minutes, so they are available within 15 minutes of the radiance acquisition. They have a global coverage over land, sea, day and night, all season. But of course, the global coverage implies also that they include some very challenging scenarios. For example, we know that cloud detection over very bright surface like surface covered by snow and so on could be very tricky. Presence of multi-layer clouds or contaminants such as aerosol can reduce a little bit the accuracy of the product. But in general, the accuracy of the product is expected to be within 5% for cloud detection. And as I said before, the resolution is the native 500 meter EUMETIMAGE resolution. This product, what are the application of this product? So these products are mainly expected to be useful for 2 kinds of application. On the one side, they will provide cloud coverage for further cloud retrieval, for example, retrieval of cloud opacity, cloud for microphysical properties, and so on. And on the other side, they can be used in a variety of other atmospheric retrieval for cloud screening, for example, aerosol retrieval, sea surface temperature retrieval, trace gases, and so on. And in this last slide, I give again back the word to Hans-Joachim for a few key points on FCI.
Yeah, for FCI Cloud Masking Cloud Analysis products, we will be operational near real-time products, providing data for the full FCI disk at 2 kilometer resolution every 10 minutes. Cloud Mask product is essential for further processing and retrieval of additional products, and the cloud analysis product will provide additional information on cloud type, cloud thermodynamic phase, and cloud top temperature and height. So that is the main things you can expect from CLM and CLA. And now back to Loredana.
Yes, about the EUMETSAT cloud mask, I would like you to take away two main points. The first one is that the EUMETSAT cloud mask is a near real-time product. It's global and has a very high resolution, which is 500 meter. And the second one is that this cloud product can be can serve application both for cloud retrieval, but also for the retrieval of other atmospheric products which need cloud screening. And with this, I give the word back to Shrika for the question. Thank you very much for your attention.
Thanks, Loredana. Thanks, Hans-Joachim. The talk was really good, but I'm more impressed by the double act. But we take the questions after the whole session. So we take a mix of questions after Phil's and the fire talk, actually.
Okay, okay.
Okay, good afternoon, everybody. Hope you can hear me. I think yes, a second. Trying to go. Oh yeah, okay, there we go. So yes, my name is Phil Watts. Responsible for some of the cloud properties, the retrieval packages within EUMETSAT in the remote sensing and products division. Colleagues here, Alessio, Loredana, and John. John, you won't see today, but Alessio and Loredana, you have or will. Yeah, sorry. So, okay. So first of all, the OCA stands for Optimal Cloud Analysis. So it was initiated by a study a long time ago with Severi and has been in quasi operations for some time. So what we get for FCI and METimage will be basically a heritage algorithm for Severi without any significant deviations. So future day 2 products will include some more enhanced properties. Yeah, so the talk is going to be along these lines. You can see the sub-bullets there. Let me just, so we go quickly on. Wanted to give a quick overview where we get our information from. And I just broke this down into starting with the simplest scenario, which is kind of an opaque, thick cloud, daytime. And the situation is very simple, but this gives the basic principles. So from the thermal infrared channels, the window channels, for example, 10, 11, 12 microns, the brightness temperature effectively represents the temperature of the cloud top, which then can be interpreted as a pressure or height given some reference profiles like an ECMWF temperature profile. The shortwave channels, which are non-absorbing in liquid and ice, liquid and solid water, they're responsive to the full total optical thickness of the cloud. And if you then use the near infrared and the shortwave infrared channels 1.6 through 3.8 in conjunction with these channels, then because the radiance at these wavelengths is absorbed by particulate cloud particles, so liquid and water particles is absorbed, and the absorption depends on the size of the particles, so that gives you then the effective radius, and that's the sort of the T cloud, or the height of the cloud, the optical thickness of the cloud, and the effective radius of the cloud is the basic suite of properties we get from the OCA. And then I just introduced some of the complications just to let you know it's not so, if the animation works, there we go. So the first thing is clouds are not generally optically thick, and then we have to deal with transmission of radiance in the thermal, of emission within the cloud from the thermal. And in the shortwave, we have to deal with reflections to and from the surface, from the cloud to the surface and back, and the same in the near infrared. So we get a little bit of help now from another channel in the thermal. So 8.7 now has a different scattering properties, so that's quite useful when the clouds get thin. Then we have, on top of that, we have an absorbing atmosphere, which generally speaking for the shortwave and the near infrared channels is just a nuisance, but so you have to just account for it. But of course we have on Severi and METimage and FCI, we have a special absorbing channel that's in the CO2 band. CO2 being carbon dioxide being a well-mixed gas, you know where it is. Therefore, the absorption in this band is quite, the effect of it can be calculated well, of course. So that gives you an extra constraint on the cloud top. So that's where we get the sort of CO2 slicing methods come from that. Finally, the main another big complication which affects principally the thermal infrared, but also the near infrared and the particle size estimation. Clouds have a lot of vertical structure. There's not much we can do with a passive imager on the sort of nuances, details of the vertical structure, but we are able to see the sort of gross effect when we have layer clouds. So we deal with layer clouds to some extent within Oka, and there we get some more help from two more absorbing channels, the water vapor channels at 6.7 and 7.3. So that's what we're dealing with, and I wanted to give one slide on the retrieval methodology. So it's as a lot of the algorithms you're seeing today, it's a 1D VAR or optimal estimation. And as Johan said in the introduction, we are trying to use all the channels where we can. And that's true for Severi. We're trying to use all the channels. That's the Severi channel set. We've never considered using the ozone channel for cloud retrievals. We don't see any reason it would bring any information. And we have a little bit of trouble still using the 3.9, but in principle, it's all in the system. The 3.9 is actually run passively at the moment, but that's the basic channel measurement set we use. When we come to FCI and VII, we'll have extra channels in the shortwave and the near infrared. And here, so just looking ahead, so this is not going to be in the day one products, but looking ahead, what we think might be useful. We've already done some studies. We don't, for the basic cloud properties, we don't see these two channels, 0.45 being useful, nor the 0.91 water vapor channel. But of course, the 2.2 from microphysics is very useful. The 1.38 is the cirrus detection channel based on a water vapor band that will be able to certainly aid cloud detection and also constrain the CTP. But we have some facility from this channel in the VII version of Oka, but not a strong input at the moment. That will come later. Finally, the most exciting channel VII only is the extra channel, I should say, is the oxygen band one, which Loredana mentioned. And that is essentially a cloud top pressure sensing channel as well, but it has its own issues to do with vertical structure of cloud. That would be nice to integrate into the whole system at some point, but that's looking ahead day 2, day 3 possibly. There's some difficulties there. But there's a standalone product from VII, which Alessio will describe in detail later. So that's where that channel comes in. So to continue the optimal estimation, so this is the measurement data set. We have for optimal estimation, then we define a state, which is the cloud state, which is the 3 basic parameters, optical thickness, effective radius, cloud top pressure. And then there's a sync variable, which is the temperature of the surface skin, and a fraction, which I put in brackets because we clamp that to be a value of 1. We never allow the cloud fraction in a pixel, that is, to be less than 1. Okay, then we need a fast radiative transfer model which connects the measurements to the state. It's called y of x. And that allows us then to minimize this penalty function. So this is the principal 1D VAR optimal estimation is essentially, in this case, more or less just trying to not exactly minimize, but get a small, or minimize the cost function, get an agreement between the measurements and the measurements calculated at your state using this fast RTM, weighted by any measurement error vector, measurement errors you wish to put in. This is a prior term, which it doesn't really apply to the cloud properties, but applies to the skin temperature. Anyway, so you minimize this function, that gives you your optimal solution. That's why it's called optimal estimation. 2 things that come out of it, in addition to the estimated state, is a value of j at the minimum of this cost function, and that's useful to know whether you've actually successfully minimized, whether there's some problem with x representing what's actually there in terms of cloud, whether there's any problems in the measurements. For example, calibration errors would show up as a problem. That is reported in the product, so that's a useful QI indicator for the entire retrieval for a particular pixel. Another nice thing which comes out of optimal estimation is a formal estimation of the error estimate for each parameter. It's actually a covariance, but we only report the diagonal, so the actual variance error in each of the parameters of the cloud parameters. So that's the error estimation at the solution. Okay, that's enough of the equations. So I'd like to just show you what the product looks like, and I think the best way of doing that is the way we look at it a little bit these days, is to look at it in a sort of a vertical cross section. So here's an image from Severi. Most of the stuff you'll see is from Severi here, because that's what we've been running for many years with this product. And if you look at a cross section here, I like to show it as represented as a vertical slice. So this is the product in the vertical. so to speak. So here's the altitude 0 to 20 kilometers, and this is the pixel number across this slice. So this is the product set as it is. It consists of phase, pressure, optical depth, effective radius, as I've said. What I haven't said yet is mentioned is the fact that we do, well, I mentioned right at the start that we do deal with multiple layers to some extent where we can see them. Anyway, so let's go through this. So this is a representation of the Occo-Severi product for this slice, this row slice through here. So you see the phase, we get liquid, ice, or multi-layer. That's the phase identification we do. There's those three categories available. And then we retrieve the cloud top pressure, and that's stored in the product as a layer 1 and a layer 2. And layer 1 refers to the top layer that's visible. So in single layer clouds like here, it's the only cloud that's there. So that's the layer 1. In that case, layer 2 does not exist. It'll be a missing value in the product. But in a multi-layer case like this, you have a layer 1 and a layer 2 reported in the product. Optical depth is exactly the same. On this plot, where I'm representing the optical depth as a geometric depth, and that's just a conversion done with an empirical conversion. There is no physical information explicitly in the radiances to give you the geometric depth, but you can relate the optical depth to the geometric depth by statistical relationships. So that's a nice way of looking at it, as to sort of visualize the product. So again, optical depth, we have layer 1 and layer 1 in in 2-layer situations, and the second layer as well. The effective radius is slightly different. It is reported the same way, but you only get the layer 1 because certainly the way the algorithm works at the moment, the radiative transfer capability is such that we cannot estimate anything to do with the effective radius of the second layer. It could be in future releases. We have new radiative transfer models going in. Technically, then we may be able to retrieve the product, but whether it'll have any value is a different matter. It's a pretty tough thing to do on the radius of the second layer. And like I said, yes, there are parameter errors reported for each parameter for each pixel. It's the diagonal of that covariance, square root of the diagonal of the covariance. So for, you'll see parameter errors, and you'll see them tend to be much larger where the cloud is thin, or where the cloud is in multiple layers. And again, there's also the pixel QI, this minimum cost value, which can be used to discard the entire pixel or not, for example, if its value is too high. This is just something to look at, really, just give you an indication. You can see this is a 24-hour cycle of a representation of the product where we've coded liquid water clouds with this sort of yellowy green case, with the brightness reflecting the optical thicknesses retrieved, and the same for ice, where it's given in the blue color. And you can see immediately there is a day-night, there's a diurnal, so diurnal effect. This is the daytime part of the image now, and you can see higher optical thicknesses. So this is the business that we cannot at night, we saturate at night. We've only got infrared channels. There's a limit to what you can get on optical thickness at night. It's around 5 to 10 or something like that. Whereas in the day, you can get much higher values. Another nice thing you can see here is the separation of layers of ice cloud here running across the underlying water. It's not really significantly affected by day and night. And another little animation down here showing some of the same sort of things in a different way. This is a vertical slice. This was a Medicane in the Mediterranean in 2017. That's the nighttime part. You see the optical thicknesses, the brightnesses here are quite low. Daytime, we get higher optical thicknesses. Yeah, that's just for a bit of fun. This is sort of empirical validation, if you like, so you get a feel for the product. Here's a strip of, again, Severi imagery here through a tropical region. This is, now what we're showing here is this slice business again, but this is actual actively sense slice from the cloud profiling radar on the CloudSat radar on the A train, showing this convective system here and cirrus clouds here. And this is the Occo product for the same slice, because we can collocate A train and Severi extremely well, of course, represented in the same way. So this is the cloud top of the first layer, cloud top of the second layer, and the depth again is being used. The geometric depth is being attained from the optical depth using this empirical classification. So visually, you can see it looks quite comparable. It's quite a nice way to validate and get a feel for the quality of the product. Some immediately show you a problem, which is a problem to most passive imager cloud type height retrievals at the moment. Not all, some, but most, I would say, is that especially for ice clouds, there tends to be a low bias of 1 to 2 kilometers, especially in the tropics and definitely mostly in ice clouds, cirrus clouds. But just to point out a few positive things, there's some nice agreement between the layer detection from the CloudSat radar and from OCA here. We're predicting 2 layers in this region as well, which the radar doesn't see. But if you look at the imagery, I think we're pretty sure it is there. It's just that the radar is obstructed by ground clutter in that region. Some words. I think Loredana introduced the sort of structure of the METimage, the METimage format for the cloud mask, and the EPSSG formats are very consistent. So there will be a reader available from PyTrol SatPy. There's an online format description on this link, so I don't think I'll go through the details. This is the same structure as Loredana showed for the cloud mask, and the same kind of, all the products are in this kind of format here. So you see CTP, the error, CTP2 for the second layer, and the error of that, etc. Let me just see. Okay, so sadly, we don't have exact consistency between the OCA products in METimage and in FCI because of various programmatic and development cycle issues. It's impossible almost to get things exactly the same. So it's a different structure. The same contents, but a slightly different structure. And what we suggest is that what we hope to move towards is that the readers will basically be a clean interface between these things, so that the user can use the reader, obtain the information in a uniform way, despite the underlying structure being slightly different. We hope. I wanted to show a little bit of validation. This is against this is cloud top height from OCA. From Severi again, validated against the CloudSat profiling radar here, and you see the basic, as I've showed before, it's quite a good match. There's about this 1 to 2 kilometer low bias in higher ice clouds. You see lots of scatter here, and this is the value of this cost function J. You can filter on J and remove a lot of this outlying scatter. And you can filter on the error estimate, which is provided with the product as well, and get a still better agreement between the radar and the product. Although, of course, you lose data at the same time. Of course, you're removing pixels from the system. Most of these pixels here, though, actually are the ones which we detect using J, and they're the ones which go into the multi-layer system. And the multi-layer clouds validate quite well as well. Well, the upper layer does. The upper layer cloud product is quite accurate. The lower layer, not very accurate, especially if the upper layer becomes optically thick. We have over the years done and are still doing various further bits of validation. Alessio is currently doing lots of work with DARDAR and an upgraded version of DARDAR. This is a combined LiDAR radar product based on A-Train, and will be available, will be possible to do as well from EarthCare in the future. So that's where we can start now validating. This is the validation of optical depth for 2-layer retrievals and single-layer retrievals. Sorry, that's the log optical depth there, in log 10 optical depth. Here's some stuff we did before a long time ago with AMSA. So this is an independent measure of the cloud liquid water path, but it's only applicable in non-precipitating and clouds over the ocean. So it's a bit limited, but so that's one other activity we did. We're currently working on ensuring the future a bit by doing validation against ground-based radar LiDAR with collaboration with the actress community. So this is a station in Bucharest, for example, and that's a kind of partly an insurance against not having a space-based LiDAR radar in the future if EarthCare is not available on time or it doesn't work or something tragic like that. But I should say we have a lot of bits of validation put together. We are currently engaged in a much more thorough reevaluation of the OCA products for Severi, at least, because we are developing a climate data record from MSG Severi. Okay, so there's nothing available on that, but we are expecting a bit more of a comprehensive evaluation towards the end of this year.
I feel
Yeah,
guilty to interrupt you. A very interesting talk, but
I need to stop. Yes, yes.
No, stop. No, speed up.
Okay, just yeah, sure.
Go
This is
through
about the
every
last.
slide.
I'm happy to skip the limitations.
No.
Oh, the limitations, a bit like Hans Joachim said, for cloud detection are kind of common to all passive imagery retrievals. So things like the nighttime retrieval of microphysics and optical properties is difficult because we don't have the solar channels. There's not much we can do about that. We're hoping the 3.8 channel will give us more information on CR on the effective radius. Similarly, if you go too high sun angles with convective clouds with lots of structure, you get non-representative optical thicknesses because the side illumination. There's not a great deal we can do about that either, but there's some possible geometric corrections in the works. The one thing we are working on and can do something about is, and we're quite close to that, is to remove this low bias in clouds. And the reason the low bias is there is because we and everybody else more or less uses a geometrically thin cloud model, and if we use thick cloud models, then the biases can be removed essentially. There are other ways using neural nets and correction, but this is the way we expect to go in the near future. And a couple of limitations with the multi-layer clouds, but nothing serious. But we wish to exploit Mike Pavlonis's method, for example, to identify multi-layers, and we will combine that with our cost function method. We've done some work on that already. And far into the future, it would be very nice to add, like I said, this oxygen band channel from VII to improve the layering, discrimination and retrieval in multi-layer clouds. That should be quite exciting, I think. So some applications, but these are really up to you, people listening, I think. So yeah, nowcasting convective storm situations. One of our main customers for VII at least will be the height assignment of the cloud track winds. That's what OCCA will be used for climate data sets and for assessment of downwelling surface radiation. But yeah, so I went on a bit too long, and questions I think will come now. Thank you very much for your attention. And I stop the share.
Thanks, Phil. Yeah, sorry, I had to interrupt you, but I think what we will do is we will take up some questions now, because your talks, the two talks are kind of in one group, but we will then take a break and go to the 5 products. If you agree, Hans Joachim, that we come back to it after the break, because we had a long session. So first I will bring the questions up for you and Loredana and Hans Joachim. Let's see. Okay, in which version of now custom software-based Cloud Mask, Cloud Top, and Cloud Top High products?
The version is 2012 version.
Okay. Mm-hmm. Okay. The next question is from Bozena. What is the reason for not using the FCI 1.3 channel in cloud mask retrievals, including this channel data and calculation should improve thin cirrus detection? This is for Hans Joachim, yeah?
Yes, we will use that channel later when the cloud mask sort of is starting just after commissioning. We will include more tests and channels which are very FCI specific. We expect the same than Bozena from that channel.
Okay. And from Andy Heidinger, from your table, there are less level 2 for FCI than Sebiri. What was the process for level 2 retirement? This, I think this was a question to Johan's first talk, yeah. Actually, yeah. But
Ricard, this is Sauli, maybe I can jump in here.
Yeah, please, Sauli, yeah. Mm-hmm.
Yeah, so what we did is we did a level 2 product survey with our member countries. And from that survey, we basically draw the conclusions to kind of stop disseminating products which were not so widely used, as there were alternative products already available from SAFs, or the quality wasn't good enough. So shortly, that's the reason.
Okay. Mm-hmm. Take a couple of questions more. Okay, I think there are a lot of questions there. this is also for the general talk. I think the total ozone is an essential climate variable, and SEVIRI provides this diurnal variation over the European region. Is there any alternative for this other than the upcoming Sentinel-4? This was for the first talk also, I think, yeah. Do you want to take this?
Yeah, I mean, there is the FCIs, so I guess it's an alternative to the FCI TOS.
Okay.
From EUMETSAT, I don't think so. Correct me if I'm wrong. But I mean, there is, for example, if you look at TROPOME, you have TROPOME total ozone as well, which is polar orbiting.
Yeah. I think this one is for Hans Joachim again. Is the first version of the cloud mask algorithm for FCI different from that for SEVIRI?
Compared to the nowcasting SAF version for SEVIRI, it's not different or not much different. There are few adaptations, but it's different from the current EUMETSAT MPEF cloud mask.
Okay. I think we should give one chance to Loredana. This question from Adam. I got confused with the timeliness less than 15 minutes on the VAI cloud mask presented by Loredana. Oh, Loredana, can you read the rest of the question?
Yes, of course. Yes, Adam is asking, there's some explanation about the timeliness, and also the comparison of the global versus VII product versus the NWC SAF mask. So Adam, this is the situation. The EUMETIMAGE cloud mask is primarily the one produced at the EUMETSAT central facility, is primarily intended to serve also the processing of other products from, for example, 3MI, Sentinel-4, Sentinel-5, and so on. Meaning that this mask is basically produced as fast as possible in order to be an input for the processing of these other products. So within 15 minutes of the acquisition of one radiance granule from EUMETIMAGE, which is only 1 minute of data, as I said, we process that and we use that for the processing of other product in the chain. This is what this 15 minute means. For 1 minute's granule, we have less than 15 minutes to process and to provide this granule for the process of other EPSSG products. This is the meaning. Now, I'm not very much aware of what is the timeliness for the nowcasting SAF product, but this timeliness refers to the 1 minute granule.
Okay. Maybe you want to answer the next one too. What is the advantage of the total? No, that's your next talk.
That's for the next
that's
talk.
the next
Yes.
talk. Yeah, definitely, we take that. And the fire talk we take later. I think the rest of them we take later, actually. I think, yeah, I think we take a break now. There are several questions actually pending, but be assured that we will provide you the answers, if not today, later. We can also take some of the questions towards the end as well. So I think we should now go for a break, a 5-minute break at that. So we meet at 15:35 CEST. See you everyone in 5 minutes. Hi everyone, welcome back. Oh, nice to see we still have all of you here. We move to the next presentation by Hans Joachim. But before that, Hans Joachim, I just want to make an announcement. I forgot to make it before the break, actually. That would have given you some time. This is about our survey that we are doing. It's also available in Slido. Stefan will put up in the chat now how to get to the survey. This is about some general questions on how you like this webinar, what things we can improve. So like I said in the beginning, this is we will have more webinars in the future, and we like to get some feedback from you on what can be improved. So please be kind enough to, not during, but after the webinar to express your opinion about this session of the webinar. Thank you very much. So with that, I give the floor to Hans-Joachim on fire products.
Yeah, hello again. It's me again, and I hope you are still on fire to listen to my fire talk. The outline of the talk is a short overview, an algorithm description, some test results, the output formats, and planned future developments. As Johan showed you, the fire product provides information of the presence of fires with a certain confidence along with corresponding fire probabilities. We limit the fires over land only, and it has a spatial resolution of 2 kilometers at nadir every 10 minutes, and will be available in 2 different formats, NetCDF and CAP. And on the right side, you see an example for MSG Severi over Greece, where you have a fire in a quite difficult situation with a lot of clouds, coastal areas, etc. And the algorithm provides us with a nice fire detection. The FCI fire detection algorithm is based on a simple Bayesian type of fire filter technique using the 3.8 and 10.5 micron channels, and it is applied every repeat cycle for all land surface pixels except for some other pixels, because we are doing pre-processing and exclude water bodies, so ocean and lakes, desert and bare soil surfaces, and coastal pixels, and for that we use a surface type map. We also exclude pixels over land which may have sun glint due to subpixel water bodies. You very often can see that over Africa. We also filtering out cold scenes with the brightness temperature test of 10.5 to identify cold clouds and surfaces, which will be excluded from the processing. And we have another filter for bare soil pixels, which is the difference between 10.5 and 8.7 micron channel. This is a test to identify bare soil which are not identified by the surface type map due to changing season and vegetation. The fire detection is a sort of probability calculations which are performed for 3 different probabilities. We compare the measurement in 3.8 micron to a maximum and minimum threshold range. We do the same for the difference 3.8 and 10.5. And we do the same for the difference of the standard deviation in these channels. And then we multiply the probabilities to get a fire probability. If the fire probability is all, just to mention, the thresholds are calculated for the first 2 probabilities are calculated from forecast data and RT-TOF calculations, also corrected for emissivity, surface emissivity. If the fire probability is 0, the processing of the pixel is stopped, and the result will be, of course, no fire. Otherwise, we separate 3 different categories with high confidence, mid confidence, and low confidence. The low confidence has to be at a minimum 0.2 or 20%. However, the user is still free to use also pixels with probabilities lower than that for their own considerations. So To have an overview, we put in level 1C data from 3 different channels. We put in dynamic auxiliary data, which is some satellite geometry, clear sky brightness temperatures calculated by RT-TOF, and of course static data. We do the pre-processing, the filtering, and the final processing of fire confidence. Here's an example for MSG severity. On the left side, we look at an image over Africa with a fire probability, all pixels with a fire probability greater than 0. There are a lot, but there are also a lot of false alarms. On the other side, having our criteria that a fire is detected if the probability is larger than 0.2, then we get quite less fires, but with a higher confidence that these are real fires. So as a statistics, we detect 28,249 pixels with a probability larger than 0%, but declare only 4,845 pixels as fire pixels. And we then distinguish between low, mid, and high confidence fires. And we do, of course, with our results, a lot of validations. Andrea Marana is responsible for this. And he has developed, for example, this classification or validation. You see, we compare our fire results with MODIS, all fire pixels, and we see that we have in blue a lot of misses, and in orange a lot of false alarms, and in green also quite a few hits. In the false alarms are mainly coming from the structure of an MSG pixel, because if you have a fire in an MSG pixels, very often the neighboring pixels also show that fire. But you also see in the center here some pixels which are very likely fires, but also not detected by MODIS nor by MSG or our fire detection algorithm. So at the output, we will get a NetCDF output with the fire result type. So no fire, low confidence, mid confidence, high confidence, and we get a fire probability with a range between 0 and 100, which means 0% and 100%. The CAP product looks like this. It's in a sort of ASCII file, and we get a lot of information. The main information is here, the location of the fire, latitude, longitude, and the radius of the pixel. And we have, of course, want to do future developments. We want to use for FCI the 2.2 micron channel, which is very sensitive to hot fires of around 1000 Kelvin. We also want to use in future the 1.6 micron channels for very hot fires of 1200 kilometers. These are very small fires, but very hot fires in general. And of course, we want to take advantage of the higher spatial resolution of FCI. We have to start at 2 kilometer resolution. And when we get the okay to use the 1 kilometer resolution data, we will do that. And of course, we are planning further tuning of the algorithm to minimize the false alarms and maximize the probability of detection. The validation of our fire algorithm will be performed by comparing our results to MODIS in 1 kilometer resolution, VIAS in 375 meter resolution, and of course the LENSAP FRP pixel fire product. And that's for today for the fire. Thank you.
think we can pick the questions from this session. Yeah. Let me just go to the questions. Oops. Show Q&A. Okay. I think let's take this one. This is on fire. Regarding fire products resolution 2 by 2 kilometer, would this product utilize the advanced resolution of IR 3.8 and or IR 10.5, 1 kilometer neither? Fires around Europe are anyhow of smaller scale.
It's of course possible to have a 1 kilometer or the highest resolution, but currently we have only the mandate to do it on a 2 kilometer resolution. But I would like and be happy to do it on the highest possible scale.
Mm-hmm. What about fires in the ocean?
Yeah, there are of course these oil platforms, etc., but the main emphasis was on land because that's what the users are asking for mainly, and therefore we are doing only fire detection on land. Mm-hmm. But it's in principle it's quite easy to change the algorithm also to fire on ocean, on oil platforms, etc. Burning ships, whatever is on the ocean. Okay. Will you explore the integration of 2.2 channel in fire detection algorithm? That's for sure. That we are doing. We are doing it as soon as we get the real FCI data in. We will explore that channel. Mm-hmm. I think I saw a question earlier on fire. You know, from after the first talk. Can't find it. These are on OCA. I think that was the question of the 2 kilometer resolution. Okay, fine. Then I think that's all with the fire today. Okay. Okay. So thanks, Hans-Joachim. Great. I think we go to Loredana now for her total precipitable water product talk.
Yes.
You ready?
Yes. So hi again, everybody. So together with my team, which include Philip Watts, John Jackson, and Alessio Bozzo, I'm also responsible of the development of total precipitable water product from EUMETSAT. Although the name is different, total precipitable water means basically integrated water vapor, so water vapor imagery. In this talk, I will present you the retrieval approach for this product from EUMETSAT, and then the format and content, and also the application and limitation of the products. So now, as we said before, EUMETIMAGE has a spectral coverage which goes from 0.4 to 13.3 microns. It is equipped with 20 channels, and among these 20 channels, there are 3 channels which are useful for water vapor retrieval. The first channel is the 0.91 micron absorption channel, which is basically located in the visible part of the spectrum. This means that this channel measurement in this channel are also affected by surface reflection and scattering due to other components in the atmosphere, for example, aerosol. So using this channel and nearby channel in the visible part of the spectrum, we retrieved the first water vapor product, which is called water vapor visible. And the name of the algorithm retrieving it is TPWVis, which stands for total precipitable water from visible observation. Then in the thermal infrared part of the spectrum, we have 2 EUMETIMAGE channels, the 6.7 and the 7.3 channel, both of them located in the O2 absorption band. And in this case, the radiance observed by the satellite in this channel is of course affected by the water vapor profile in the atmosphere, but also by emission from the surface and emission of other layer in the atmosphere. So we need to take into account here also the surface temperature and the temperature profile in the atmosphere. The algorithm based on these two infrared band is called TPW-IR, total precipitable water from the infrared observation, and the product is called VII-O2 water vapor infrared products. Now, what is the retrieval approach for this product? The retrieval is common to both products and is based on a 1D-var algorithm. So a quick reminder on the 1D-var approach. So basically, the approach consists in to minimize this the so-called cost function, which is basically depending on the difference between the measurement and the simulated measurement from a proper radiativity transfer model, or also called formal model, which can basically take into account the general condition of the atmosphere and the surface at that moment. The other terms of the terms of this const function in our case are the following. So the measurement vector y contains basically the instrument measurement. In the case of TPWVs, these are all the reflectance from 0.4 to 1.2 micron, including, of course, the water vapor absorption band at 0.9 micron. And in the case of the infrared retrieval, these are brightness temperature from 3.7 to 13 micron, including the two thermal infrared water vapor absorbing channel. Then we also have, of course, in the retrieval, the SY matrix, which is basically the error covariance associated to the measurement, which contains all possible source of errors. So channel noise, channel co-registration error, biases, and so on. Then we have the state vector, which is basically X, the quantity to be retrieved. And here we have the water vapor profile, of course, which is what we want to retrieve. But in the case of the visible retrieval, we have also the surface BRDF and the aerosol optical depth, because they can contribute to the observed reflectance in those channels. And then in the case of the infrared, the water vapor profile is retrieved together with the temperature profile and the surface temperature, because we have this emission contribution from surface and atmospheric layer. The formal model in both cases is RTTOF. So RTTOF provides the simulated radiance depending on the input value of this state vector. And the initial values for the state vector and associated error are taken, of course, from the ECMWF forecast. Now, so starting from the EUMETSAT measurement and this auxiliary file, including forecast, surface albedo and emissivity, maps of aerosol, which are retrieved from the CAMS database in our case, the algorithm starts an iterative procedure. So at each step of this procedure, the algorithm computes the cost function and then compare it with a threshold. If the cost function is less than the threshold, then the iteration is stopped. If the cost function is above the threshold, then the state vector is adjusted by a given delta, and then the formal model is run again with this adjusted value, and so on until conversion is reached. Finally, when conversion is reached, from the final state vector, we extract the humidity profile, we integrate it, and we retrieve the total column water vapor. The product themselves are following the same structure as any other EPSSG product, as I said before. Also for this product, we have already test data available in our website and also readers available in Python. The two products are identified by the identification VII-O2 VWW for the visible product and VWI for the infrared product. The spatial resolution of the product is 3 by 3 pixels. So the water vapor is not derived per pixel, but for aggregating the pixel in a 3 by 3 pixel box. To this box, we gave the name field of regards, and the extension of one field of regards is basically 1.5 kilometer another. The SWOT again is about 2,800 kilometers, and in each 1 minute product, you have about 1,000 per 300 field of regards. The structure of the net CDF is the same we have seen for the EUMETIMAGE cloud mask, so with the 3 main groups. And in this specific case, the data and quality group, which contain the specific parameters of this water vapor retrieval, have the content which is listed in this table. Basically, the time of the observation. Then for each field of regard, you have the geometry and the geolocation. And finally, for each pixel regard, you have the retrieved total column water vapor in kilogram over square meter, the associated error in percent, the retrieval cost, because this is a good indicator of the quality of the retrieval, and then another indicator which gives the difference between the retrieved water vapor and the one predicted at that time and for that location by the forecast, which we find out to be of particular interest for the users of this product. And the rest is again flags indicating the quality of the product in terms of number of field of regard with high error or high cost, the size of the field of regards, and so on. Now, pro and cons of this product. So these products are near real time. They are distributed 24/7. The timeliness is about 30 minutes, meaning that they are available 30 minutes after the acquisition of the L1B radiance file. The coverage is global, so over land and sea, day and night, all season. But we have to remember that TPWVs is using visible observation, so is only available during daytime. And both algorithms are retrieved in clear sky only. So the pixels or field of regards are basically cleaned before the retrieval to exclude those pixels that are contaminated by clouds. This means, of course, and here we have the limitation of this algorithm, that if by any chance the cloud mask is wrong and the cloud and the pixel is affected by cloud or aerosol or other obstruction, the algorithm is less accurate because our model is based on a clear sky model. And finally, for the TPWVs, we have to take into account that the signal coming from the dark surface like the ocean is very low, so the algorithm managed to run, but with very high error. Anyway, altogether, the requirement for this product is 5% accuracy into the retrieved total column water vapor. And the resolution is that we get right now is 1.5 kilometer, which is well below the threshold that was set by the user, which was 10 or 3 kilometers. So we are already meeting this requirement. The algorithm has no continuity at EUMETSAT because no water vapor was retrieved from previous polar mission. So it is based basically on heritage from MODIS and MARIS. And the main application of this product, in our view, is the following. So what you see here on the left is an ECM, is a forecast prediction for total column water vapor in the atmosphere. And you can see that the resolution, unfortunately, is not high enough to detect features, water vapor feature of the order of 1 to 4 kilometers. Instrument like EUMETIMAGE or MODIS or other instrument, for example, the current Sentinel-3, they are able to retrieve a feature with lower resolution. So as you can see, the resolution is much improved. So the hope is that this product can help improving the forecast model for the identification of this very low feature of water vapor, which we believe are concentration in the boundary layers where the onset of severe weather condition can be identified. And this onset as of the order of 1 to 2.5 kilometers. So this is the range where we are interested into retrieving water vapor imagery, which cannot, and this resolution cannot be achieved at the moment with sounders, for example. So this is the only way. In this last slide, I would like to show you a comparison between our water vapor retrieval based on MODIS and the MODIS operational product. So this is the total water vapor retrieval on visible band. There is an equivalent product from MODIS as well. As you can see, we know already that our product performs quite well in comparison to the MODIS one. Of course, we are still into the validation process, and we have to wait real data to assess this. But for now, we are quite confident that we are performing as good as MODIS. And finally, what I would like you to take away from this product is that the products from EUMETSAT are near real-time product. They are available globally, and they provide the integrated total column water vapor. The resolution is very, very high, 1.5 kilometer. So, and we believe that this resolution could be essential to improve the prediction of the onset of severe weather conditions. And finally, I would like you to remember that these products are retrieved in clear sky only. So the presence of cloud or undetected cloud or aerosol can degrade the quality of these products. Finally, for the TPW-Vis product, you have to remember that over dark surface, the retrieval, although it's present, is less accurate due to the very low signal of this dark surface. And with that, I thank you for your attention, and I give the ball back to Shrika. And I don't know if we are going to do the questions now or later.
I think for you, maybe it's better that we take the questions now, and then we go to Alessio's talk, and then take a couple of questions for Phil and Alessio together. Okay. And then we break for everyone, we break then for about 4 minutes, and then come back for the last talk. That's the current plan. I mean, we are modifying the plan in between just to get everything right. I think I will bring your questions up, Loredana, now. Just a minute.
So I think I remember already 2 of them.
You're prepared, I guess.
Yeah.
I think
so.
Which is the one you wanted?
There was yes. First, why we have 2 separate products. So there is a double reason for that. The first one is historical. The second one is due to continuity of the product. So historically, for example, from MODIS, although MODIS is equipped with the same visible and infrared water vapor bands, the 2 products are retrieved separately. And this is because we are using different wavelets in this product. So you might expect that the different wavelets are peaking quite differently in the atmosphere. So you can have a bias between the 2 retrieval. So a small amount of water vapor that is not detected by the other algorithm because we are peaking at different height in the atmosphere. Now, so this is the historical reason it was done like that. So the initial requirement for EUMETSAT taking into account MODIS heritage was 2 separate products. The other reason is that if we go for 1 product, and we could do that because our 1D retrieval allows to put together all measurements, we have a discontinuity between day and night because the visible bands are not available during day, so they have to be switched off. And at night, during day, you have both visible and infrared. So we think that this could create a slight bias between day and night that the user might not like. So that said, we have in the plan for the day 2, so after the commissioning, to merge these 2 products in one, to test it, of course, offline first, to see how the user reacts to it, and then if the reaction is positive, to integrate it as an operational product. But for day 1, they will remain separate.
Okay.
The second question, yeah.
Which one did you want to take? It's the advantage.
For example, yes, what is the advantage with respect to MODIS? So with respect to MODIS, the products are very, very similar. They are based on the same bands, both for the visible and for the infrared. The only advantage that I can tell you is that for the visible case, MODIS at the moment assume a constant contribution from aerosol. In our case, this contribution is not constant, but the right value of aerosol load is taken granule by granule from the corresponding CAM file. So from the Copernicus retrieval. So this could improve a little bit the accuracy. While for the other product, from the infrared product, MODIS resolution is unfortunately only 5 kilometers. So it is a grouped product. It is as a resampled product at 5 kilometers, while our product would be 1.5 kilometers at the beginning, hopefully less for day 2. So we have a higher resolution in the infrared.
Okay, thanks. I think there is maybe one more on this.
Yes.
Will there be classification
for
low, mid, high level?
No, unfortunately not in this product. The only quantity that is given in the product is the total integrated water vapor all over the atmospheric layer.
Okay, good. Thank you, Loredana.
Welcome.
Maybe there are other. Oh, this. Do you want to answer this one? Why not use?
Why not use
temperature difference 12-10 for 12 and 10 for low level water vapor?
10 and 12 for low level water vapor. Didn't retriever use on? No, so that maybe I was not clear enough. The TPWIR retrieval use all bands between 3.7 and 13 micron, including the 2 water vapor band, but also other bands like the 10 micron, the 8.5, the 12 micron. So the final retrieval is basically adjust on the basis of all these measurements, not only the water vapor absorption channel, of course.
Okay. I think it's so then. Thanks, Loredana, for the talk and for answering, I think, all the questions. But yeah, if there are remaining, we would come back. So I think with that, we move to Alessio for the cloud top pressure product using the oxygen A band.
Okay, good afternoon, everyone. My name is Alessio Bozzo, and I work, as was mentioned already by Phil, together with Phil and Loredana here at EUMETSAT, mostly on cloud and radiation product, mostly on FCI. But today I'm gonna talk about our cloud top pressure retrieval product for EUMETIMAGE using the oxygen A band. So is cloud top pressure retrieval different from what we saw already for OCA, what was presented already by Phil. For this material, this presentation, I have to thank especially the team at Igeos and Deloitte, Mathieu Compagnie, especially because that was part of a project that they run for us for testing the capability of this type of retrieval for VII. So very briefly showing the physics behind how such a retrieval would work. So here's the physical basis. So in this case, we are looking at the daytime product because we need the solar radiation. So we're looking at the backscatter solar radiation from the top of the clouds. And in particular, we are looking at two particular channels, BII channels. So the 7.52, 0.73, 0.763, 0.752. So these are two channels in the near infrared end of the visible spectrum. One is a window channel, so with no absorption, and another one has a relatively strong absorption from oxygen, and this is called the oxygen A band. And this algorithm make use of a differential, basically comparisons of the backscatter photons within these two channels. And comparing the absorption path of the backscatter photons, is possible to retrieve the top of the cloud. So this is how it would work in a theoretical world. So we expect the photons from the sun to be scattered back from the top of the cloud and be sensed by the satellite. And comparing the signal received in the two channels, we are able to say to retrieve the cloud top. Of course, the situation is not that easy. And what we actually see in reality is a certain penetration depth within the cloud layer. And we have cases where photons enter in the cloud and are multiple scattered and then back to the satellites, or they'll be able to escape from the base of the cloud, being scattered back from the surface and back to the satellite. So such a retrieval has to take into account these problems. And we have to take into account this capability. We have to take into account these problems, in particular the surface reflection, the cloud vertical structure, and the optical properties of the particles within the cloud. We are looking again, as we saw multiple times in this previous presentation, at optimal estimation algorithm, so variational algorithm. So in this case, we're starting from observations, and again, we look in observation in these two channels around 0.7 microns, one in the absorption band and one in the window. And then we also use other two channels in the visible, so two reflectance, two channels with the reflectance, one in around 0.7 microns and one around 0.8 microns over land and over ocean. That gives us information of the photons that are scattered back from the surface. Then we have assumptions about the vertical structure of clouds. And this is computed with a data set of actually observed structure within the clouds from active instruments, LiDAR and radar. So we have a set of vertical structure of clouds. In this case, we're looking at the extinction within the cloud for different types. And so that gives us some baseline that we can assume for different type of clouds. And that tells us something about the penetration depth of these photons. And then we have our forward model. So how we connect the observations to the parameter that we need to do the radiative transfer simulation with. So in this case, a set of lookup table are pre-computed with a radiative transfer model, is Art Deco in this case. And so we have a set of lookup table that connect optical thickness and cloud top pressure and different other parameters to the observations. And basically, these combined together with the assumption in the vertical structure of the cloud, they are combined together. And again, we saw this cost function a couple of times already. So we're going to minimize the cost function, take into account these observations. So the observation in the oxygen band plus the surface, and a state vector that in this case is the cloud top pressure and the optical thickness. And then we minimize this cost function to find the optimal cloud state that matches the observation. At the end of the retrieval algorithm, and the main variable that are retrieved are the cloud top pressure and the cloud optical thickness, and both of them coming with uncertainty because we are looking at the optimal estimation algorithm, so we can compute the error on the retrieved variable. And we also have extra information available from this algorithm, in particular a flag that tells us when we are dealing with multi-layer flags, multi-layer clouds. And though I'm going to show later that is a tricky situation for this algorithm. And we also have a possibility to estimate the geometrical thickness of the cloud, or by construction the cloud base, because we have this assumption in the vertical profile of the clouds. Details of the inner working of this algorithm are available in this report available on the EUMETSAT website. So the characteristics and the application of the product. So again, is a product that provides cloud top pressure and cloud top height, and cloud optical thickness with relative uncertainties, and the multi-layer flags plus the parallax situation. Is a near real-time product, and of course is a day only, because by construction, the timeliness is less than 20 minutes. And the scenarios are or day and over sea and over land and over coast and all seasons. So there are no limitation apart from that is at daytime. Challenging scenes, I'm going to show a couple of results later, is clouds that are particularly thin and multi-layer clouds, and where we have a high contamination from aerosol. Application, well, is a mostly cloud top pressure and cloud optical thickness retrieval, so can be seen as a support to retrieval from other instruments, but is also an alternative retrieval of cloud top and cloud optical thickness. And as Phil mentioned before, it can complement OCA in a sense that they sense slightly different observations and they can be compared together and combined together to optimally retrieve perhaps the cloud fields. Of course, in the future, this type, similar type of algorithm, or this type of the information within these bands can be included in OCA, as was mentioned before. And also it could be a potential support for cloud height assignment for AMV, in particular for the AMV using shortwave channels in VII. Just an overview on the content of the product. Will have the similar structure as saw before for the water vapor. In particular, so we see here the main variable are the optical, the cloud top pressure and cloud optical thickness, all with the associated error. Again, together with the associated error and the cost function at the end of the minimization procedure, we have some quality indicators of the retrieval. I'm going to show a couple of examples computed with proxy data. So in this case, we're using MERIS observation, which has similar bands within the oxygen A band for two cases. So this one is a case with low stratus like clouds over the ocean, and this is more complex deep convection cloud with low clouds and cirrus clouds. And that is an example of a cloud top height in the two cases. This structure, these bands are due to stray light effect in MERIS, so it's nothing to do with the algorithm in particular. So we see here the retrieval of cloud top height of homogeneous height over these stratocumulus clouds, and a more complex scene here on deep convection. Another example here is we're looking at a cross section of a cloud. On the bottom panel, we see the reflectance, so the observation from the cloud LiDAR. So it's the backscatter from the LiDAR that shows the vertical structure of the clouds. And we see in this case a high cloud, relatively thick, covers almost all scene, and on the left-hand side we see a low cloud underneath this ice clouds. On the top we see the retrieval. In green is this retrieval with the oxygen band, and in red is MODIS retrieval for the same scene, and in blue is the operational retrieval with the polder parasol. We can see they all compare fairly well. Of course, the difference between the MODIS cloud top height and this oxygen band cloud top height is they use completely different information, infrared band for MODIS, while in this case we have a visible band with different assumption within the cloud. So we do expect by definition, by construction, as the two algorithm differences, but we can see they're all comparing relatively well. And in this particular case, this oxygen band retrieval captures the cloud top height for the two parts with an estimation of the cloud base as well. Of course, the part in the middle where we have a two-layer situation, all algorithms tend to struggle a bit. And in this case, for this algorithm, that pixel would be flagged as a multi-layer, so is a lower quality for that part of the retrieval. And this last example is using synthetic data, so is synthetically computed VII radiances over Europe, and using realistic cloud fields from AVO-HRR and vertical profile from CAMS and ECNWF. At the bottom, we see the truth for this scene, which is the cloud top height from AVO-HRR. And on the top right, we have the difference between this retrieval with oxygen band with respect to the truth. And we can see that most of the time, values are around 0, so they do compare very well. the most difficult regions are where clouds are particularly thin or broken with a no full cloud coverage. But if we look at the histogram at the bottom right of the differences between the truth and the retrieved cloud top height, we see the most of the pixel agree very well. And as a last point, this is an evaluation against CloudSat and Calypso observations over a full year, 2008. And the bottom line, I'm not going through the whole table, but basically shows a different cloud height, cloud type, and different with different capability of the retrieval. And what we see that given a certain altitude class, generally the algorithm tends to perform better for thick clouds, and we see stratus and nimbostratus tends to have the lower error. Given cloud optical thickness, cloud top height for low cloud tend to be underestimated, and cloud top height for high cloud tend to be overestimated. And at the end, again, higher uncertainty is expected in a multi-layer situation and thin, low optical thickness clouds. This is it for this brief overview on this product.
Thanks, Alessio.
Thank you.
I think we can pick some questions for you and also for Phil now. Let's see what you have. And Regis says, agreed that we can go ahead with a short break after this. So let me just bring up your questions. Phil, are you there?
Yes.
Okay, I have some questions for you. Okay, yeah, maybe you want to pick your questions or
Yeah.
Which one?
You can take the first one, the Calypso. Yeah, we have done
yeah, okay.
comparisons between Oka and Calypso. Yeah, so generally it's a similar story to CloudSat, especially in the extratropics. In the tropics, Calypso is much more sensitive than CloudSat to small particles and very thin cirrus high in the tropics. So we get a bigger bias. I think that everyone gets that experience with comparisons to Calypso. What we're doing, what Alessio especially is doing now, is using the DARDAR product, which is a sort of combined LiDAR radar product. So we're not so distinguishing so much between the two active instruments. But yes, we have done those comparisons.
Okay.
Hope that answers the question.
This is for Alessio, right?
Yep.
Yeah.
Yes, I agree. It's very important for aviation. We don't actually have much experience from that community. It actually would be very interesting to have more interaction. I don't know if with similar cloud top pressure products there have been any particular feedback from aviation community before, like Oka and Severi or other instrument. I don't know if Phil, you have any.
Well, we haven't explicitly extracted the base cloud base height from the other from the other algorithms to this point.
Yeah. So in this case, I have to stress that the cloud base from this particular algorithm is not directly a retrieval. Is an estimation given the set of assumption in this vertical profile that we use. So it gives some information. Yeah, it has to be treated with a bit of caution, but yeah, definitely could be an interesting interaction.
Okay. There was one more. There were a couple more questions on Oka that I saw before. These two.
Yes. The background errors, I think that probably refers to what errors are attached to the background in the prior input in the optimal estimation, I guess. So effectively, the main cloud parameter, so the cloud optical thickness, the cloud effective radius, and the cloud top pressure in the single layer retriever are not constrained at all. So there is an error technically in there. It's just set very high, like 10 to the 6 or something. So it doesn't have any constraint because there is no real background information coming in. If you saw in the state vector, there's also, we have a skin temperature to constrain, to take account of the effects of errors in the forecast skin temperature in the whole problem. And there we do apply a constraint, a fairly reasonable one. So 1 Kelvin over ocean, 6 or 5 over land. But the cloud parameters themselves are not constrained. However, the one caveat is that when we go to the 2-layer retrieval, because the information content is getting a bit thin for 2 layers, we do find we have to put in some more empirically stronger constraints on the retrieval. So when we go to 2 layers, for example, if I remember correctly, the upper layer cloud pressure is constrained around somewhere below the tropopause, plus or minus 100 hectopascals. It's not allowed to wander too far. So there's various levels of constraint used in different circumstances, but in the single layer basic retrieval, effectively the cloud parameters are not constrained.
Okay.
Yep.
I think we take the rest of the questions maybe towards the end, if because we need to have another short break, I think, for 4 minutes. But let me also ask the participants, please, to express your opinions in the polls. And then we come back in 4 minutes at 16:31 for Regis Body's talk on wind products, AMV products, actually. Thank you. Hey, welcome back, everyone. Thanks, Regis. You have already put up your slide, so you can start, actually.
Good afternoon, everyone. I am Regis Bord. I am a remote sensing scientist at EUMETSAT, and I am responsible for the wind product. This includes the atmospheric motion vectors extracted from imagers, and also the current investigations that are done on development that are done for the 3D wind profiles extracted from infrared senders and LiDARs. The co-authors that work with me on wind products are listed here. Does not work. Oh, okay. So we start with the MTG FCI algorithm. The prototype code has been developed from MSG operational processor, and comparison of the performance have been done against the MSG atmospheric motion vector operational algorithm. Scientific validation has been done also using GeoCompSat data and in collaboration with colleagues from KMA. The results of this scientific validation has been published in a paper 2 years ago in remote sensing. And we have also tested the algorithm during the third AMV intercomparison study that has been done using Imawari data. The results of this intercomparison study have been published also in remote sensing journal 2 years ago. we currently perform verification against reference code that is prepared by industry, and this activity is going to last until 2021, 2022. Then will come the commissioning of MTG FCI AMV algorithm and from 2022 to 2023. And as the upcoming work, we also plan to participate to force AMV intercomparison study. This time we will use GOES 16 data, and it will start later this year. So at the end of this AMV intercomparison study, the MTG FCI prototype code will have been tested and used with GeoComSat data, Imawari data, and GOES data that are the new generation geostationary satellites that are quite similar to MTG FCI. The MTG FCI prototype code for the atmospheric motion vector is largely based on the MSJ AMV processor. There are, however, some difference. We will use only 3 images instead of 4, which allow us to provide to user a half or real product. The center image of the 3 image will be used as reference for both the time and location, and we will then process backward and forward tracking. There will not be any intermediate product averaging anymore, and the second component will be used as final product. The AMV will be derived from channel visible.8, infrared 3.8, whatever per channel at 6.3 and 7.3, and the window channel at 10.5. It is pretty similar to MSJ Severi. Only the infrared channel at 3.8 will be used in addition during night time. The data will be provided to user using the new AMV buffer sequence that has been endorsed by WMO 2 years ago. And using this new AMV buffer sequence, we have the possibility to include in the output file more information that can be useful for users for assimilation. The cross-correlation contribution to cross-correlation method is used for tracking. And the final AMV coordinates will be set to the position of the tracked feature and not at the position of the center of the target box as it is done currently. Finally, we will use the optimal cloud analysis product to set the altitude of the winds. This slide summarizes some comparison for the performance of the algorithm against current operational code. We show on this slide the average numbers of AMV per channel for winds that have been set with a QI quality index larger than 80. And you can see that slightly more AMVs are extracted, especially in visible channel and in the infrared window channel for MTG processor. I do not insist on that. This slide shows the vertical distribution of AMV speed bias as a normalized root mean square for the AMVs with a QI larger than 80. You can see the MTG results in red and the MSG result in blue. Like the two algorithms are very similar, we obtain also very similar characteristics and performances, especially for visible and infrared channel. You can see that the performances of MTG seems to be slightly better. This slide shows the comparisons against GeoComSat. This is extracted from the paper from our colleague from KMA, Mr. O. On the left-hand side, you can see the pressure distribution for both GeoComSat and MTG prototype code. The results are very similar, and there are some differences at low levels because the setting of the altitude was different for the two algorithms. MTG used the cloud product developed at EUMETSAT at the time of the study, but at this time the cloud product was not very good. And the EUMETSAT algorithm did perform separate assignment process. On the right-hand side, you can see scatter plot of MTG of the speed of AMVs against forecast fields for both MTG and EUMETSAT. These results are shown for the visible channel, and it is the same for infrared channel. The results are pretty similar. Now, some words about PSSG EUMETIMAGE AMV status. The prototype code is developed. It includes AMV extraction from 5 different channels: visible.8, infrared 3.7, water vapor channels at 6.7 and 7.3, and the wind channel at 10.7. It is very similar to MTG FCI. The data will be provided to user community with a new AMV buffer sequence, and we provided already a first version of the dataset that has been distributed in September 2019, and it has been made available to user community. You can see an example of on the right-hand side of AMV derived from a simulated EUMETIMAGE band in the window channel. We received feedback on this first version dataset from SIMS. DevSantech made a quick comparison with MODIS, and it shows a good agreement. Future work for the PSSG EUMETIMAGE AMV will be the verification against reference code from industry. This activity will last from now to 2023, and there will be the scientific validation of the product. The main difference, the PSSG EUMETIMAGE algorithm has been developed using the same framework than the Sentinel-3 SLSTR AMV algorithm recently developed at EUMETSAT. And you can find all the detail of this algorithm in the recent paper published in Remote Sensing earlier this year. The main difference between this new framework and the actual operational AMV framework for IVHR is that the data are first projected on an equal area grid. The projection tool has been developed internally at EUMETSAT, and the AMVs are derived from the resulting images. This was necessary for EUMETIMAGE due to the bow tie effect that has been described by Pepe yesterday. On top of standardizing the approach for all the LEO sensors, this method also allows to derive winds outside the frame of the reference image, which increase significantly the AMVs that are extracted from LEO satellite. On this slide, I summarized the characteristics of AMV production for SLSTR, EUMETIMAGE, and AVHR. You can see information on the resolution, on the swath width, and geographical area where the AMVs are extracted. The main benefit and advantage of EUMETIMAGE will be the extraction of AMVs in several channels, and especially in the water vapor channel at 6.7 and 7.3, which are a big request from user community. For the time being, only MODIS is going to extract water vapor winds over polar areas, and EUMETIMAGE is supposed to continue this capability after when MODIS will not work anymore. My last slide shows the comparison made by DevSantech at SIMS. On the left-hand side, you can see MODIS and EUMETIMAGE polar winds extracted from infrared channel over the Arctic. And on the right-hand side, you can see the scatter plot of MODIS and versus the EUMETIMAGE collocated winds. And you can see that the agreement is pretty good from a small to large wind speed. This is a very encouraging result, especially considering that this comparison include the first version of the dataset extracted from simulated EUMETIMAGE imagery. And I will stop here, and I thank you for your attention, and I am happy to answer to any question if you have.
Thanks, Regis. Yeah, quite nice to see the AMVs from GEO and Polar orbiting satellites. Also, you had this comparison with SLSDR. Great. I think we can take up some questions, right? Let's see. Sorry, they're coming up. I think I see a question in the chat, but we can take that later. We first take the question. Yeah. Oh, I think that's a question. Is there I don't know, somehow the most recent question is not coming on the top, although I have set it up like that. But yeah. Okay, one question is about the slide comparison with MSG. Did you see that, Regis? Comparison.
Yes, I see it. Yes. Comparison with instead of
the water vapor channel with 7.3, it should be water vapor channel 6.3, 6.2.
Just let me check. Yes. Yes, that's true. Yeah.
Okay. That's a clarification. I think okay, I just browse, okay? I think that's the one. For FCI AMVs, are the three images used to derive AMVs overlapping with the three images used in the next time step or distinct from each other? In other words, is there an AMV product every 30 minutes or every 20 minutes?
It's two product per hour, but all the images are used. Then we use -10, 0 hour, +10, and then +20, +30, +40. So all the images are used, but it's two different products. There is not any overlap.
Is there a metric to tell whether MODIS or METIMAGE wins are better? What about VIIRS?
We will certainly use VIIRS for validation, but for time being, we don't have any METIMAGE wins, so it's difficult to say what will be better until we will not use the real images.
I think I tick them off then. I don't see actually anything else. Okay. I don't see any MV questions there anymore, but we have some other questions. But thank you, Regis.
Thank you.
Thank you very much. So everyone, we have some more questions. So I request all the panelists to be ready. We can take some of them. We have, yeah, we are at 4:45, but I think we can spend something like 10 minutes for those interested to give some answers to the questions. Okay, I'm now confused because there are a lot of questions. Maybe the speakers, you can come up when I read the question, who wants to answer, yeah? Is there a classification for a supercooled water clouds important for aviation, for instance? Thank you.
In the CLA, there is no classification for supercooled water clouds. And for OCA, I don't know. Perhaps Phil can answer.
Yes, no, we have nothing explicit either, actually.
Okay.
I have to say.
There's a question from Olivier Sievers. Cloud phase, slide 14. What are mixed phased clouds processed as? I think this is for Hans-Joachim, right?
Yes, in the current scheme, there is no mixed phase cloud phase. We either declare it as a water or as a ice phase cloud or as this unknown. if you don't really can put it in the bin, water or ice cloud.
Okay, I think this is also for you. Did you have a mainly thick clouds in your slide?
Yeah, mainly thick clouds are sort of, we have the expression for thick clouds where the signal comes from the most upper part of the cloud. And then we have the thin cloud, ice clouds, where you have some of the signal coming from surfaces below the cloud. And mainly thick cloud means clouds where no signal comes from the surface, but from the mid and lower part of the cloud. So the signal is not from the upper part or highest part of the cloud, but from somewhere in the middle or at the lower part of the cloud.
Okay. Given the limitation, how successful is a cloud mask in detecting radiant fog?
We have sort of two tests for that, which is one is 3.8 minus 10.5 micron channel and also 8.7 minus 10.5 micron channel, which both can detect fog. How good that is, I cannot really tell because we haven't had any comparisons with other fog data. But we detect low-level fog because in some areas it's very successful to have low-level clouds of fog with a 3.8 micron channel minus 10.5 micron channel, and in other areas the 8.7 minus 10.5 micron channel detects sort of the remaining fog. Especially in the northern or northeastern part in Europe.
Okay, thank you. I think, Phil, that's for you. Is the empirical formula used for converting this available somewhere?
Well, it could be available. It's been obtained from results that Higios did for us for the auction band retrieval, actually. So they analyze the I simply parameterize that into a small function, so I could make it available if anyone's interested. But it's not peer reviewed, refereed or anything. It's just taken out of a report. So you're welcome to it, but it would be just on that basis. Yeah. Please contact me if you need.
Do you also want to answer this? What software do you use for the simultaneous operational presentation?
That's software. This is the software I developed myself in IDL. It would be very nice. We've been trying to get it perhaps made more operational, or to be used as a sort of an operational display. But no, it's just stuck in my personal IDL code at the moment. If it could be put into SAPPI, that would be excellent. So I don't know if that question is also an offer. If it is, then also contact me.
This is for processing time requirements for the EPSSG now casting SAP cloud mask is.
Yes, that's basically a continuation of our discussion of the timeliness of the EUMETSAT cloud mask. So it's true the cloud mask from the SAF is much faster, but you have to take into account that the EUMETSAT, the EUMETSAT cloud mask, the one that we produce centrally, cannot be that fast, cannot be 1 minute because our threshold computation is based on RTTOF. So we need to run an RTM before running the cloud mask. That's why we take longer, and that's why there is this limit of 15 minutes.
Okay. Thanks, Loredana, for the clarification. Again, there's one more question. Is it technically possible to produce ASR product for EUMETIMAGE? Who can answer that?
I can answer, and yes, technically it is possible. What you need is basically the radiances, brightness, temperatures, and reflectances, which are available for EUMETIMAGE, and then you compute statistics in your given field of regard. And if you want the different categories, you also need cloud mask and some information about cloud height, but that would be available from Okka and a cloud mask. So yes, but not it won't be disseminated from when operations start, but technically yes.
Okay. Thanks, Johan. That completes our list of questions. I stopped sharing, but I thank everyone for being present here, though it took a bit longer than we actually anticipated, but we finished before 5. That's an achievement. But I also want to thank all the speakers as well for the excellent talks, not just for today, I mean, for the last 2 days as well. So thanks, everyone. It was wonderful, really, really very cooperative and nice guys out here at EUMETSAT. You presented really, really materials that are very useful for the users. So I thank all of you, a big hand to all of you. And thank you for the participants as well. We really appreciate that you took your time to listen to these talks. Also, like I mentioned earlier, the links, I see that there's a question already from Andy Hedinger. Yes, we will make available all the presentation slides. We will make available the Q&A with the answers. We will make the recordings also. So all these 3 will be made available. And just if I can make some advertisement, we will also have more webinars coming, but the next one is on the EPSSG 3MI mission. It's happening next week on 14th and 15th, so Monday and Tuesday. Just go to EUMETSAT webpage and go to the current events. You will see how to register for this event. That's all from me today, but I would also like to thank Stefan Budzinski. Stefan, would you like to say one sentence to end before we end?
It's been great. You've done a great job in moderating.
Thanks, Stefan. But yeah, we did it together. Thanks, everyone. See you for the next one. Bye-bye.
Thank you. Bye-bye.
Bye.
Bye-bye. Thank you.
Thank you. Bye.